We've already seen in this unit that force has a very strong connection to acceleration. Specifically, whenever there is a net force being applied to an object, we know that it must accelerate. We also saw when we talked about Newton's first law, though, that mass had something to do with this as well, because objects with a larger mass, for example, had a greater amount of inertia. It was harder to cause them to accelerate, cause them to change their velocity. So we now know that force, mass, and acceleration all have a strong relationship when we deal with forces in general. And so we're going to just look more specifically at how these compare in a particular situation. So we're going to start just with the middle column here. And this middle column in your chart will represent the regular average situation. So you can imagine it's a very simple little bus, or maybe just a trailer with people in it or something like that. And so normally I'm going to pretend that this bus carries 2 passengers in it. So there is my incredibly artistic representation of my 2 passengers. And that's a bus at regular capacity, we're going to say. So what this chart is saying that we apply some amount of force. The bus overall has some amount of mass, and that causes it to accelerate at some particular rate. Now, we don't even know what those specific values are, but just if we use those letters to represent some amount of force, some amount of mass, and some amount of acceleration, we can see how the rest compare to that. So now let's look at the other 2 columns. If we go to the left-hand column now, in that case, we're dealing with a situation that is supposed to be representing 2m. Well, 2m means twice the mass. So twice the mass would be, well, let's make it simple, and we'll draw 4 passengers. So this would be a bus that is now at twice the capacity, or twice its mass in total. Well, through experiments, what's been noticed is that when an object specifically has twice the mass as a previous situation, it ends up accelerating at exactly 1/2 of the acceleration rate. Or in other words, it's 1/2 a. So if the acceleration rate originally was just some value a, it'll be exactly 1/2 a when we double the mass. We see the opposite happening when we look at the final column. Now we're going to cut the mass in half. So now instead of 2 people on our bus, which would be regular capacity, now let's imagine that it's just half of that, half the mass. Well, what we end up noticing again through experiments is that we get double the acceleration. Half the mass gives us twice the acceleration. And so there's not only a connection between those variables, you can see that there's a very strong mathematical relationship. When one multiplies by 2, the other divides by 2, or cuts in half. This is what we call proportional relationships. Now, specifically, we can talk about what is proportional directly to one another and what is inversely proportional to one another. And that's what we'll talk about below. We can actually start by just stating something that we already knew. And don't worry so much about the fancy symbols that you see here. Something that we already knew was that acceleration is proportional to the amount of force that's being applied. And we've already talked about this, that the amount that I accelerate depends on how much force gets applied. So stronger amounts of force lead to a stronger or a greater amount of acceleration. So that means these variables are directly proportional to one another. So when we write the 2 variables, a and f, for acceleration and force, to say that they're proportional to one another, meaning that when one increases, the other increases in the same mathematical way, to represent that, we draw a little symbol, kind of like a backwards Jesus fish, and that is the Greek letter alpha, and it's used to represent proportional relationship. So that statement is a mathematical statement that says acceleration is proportional, directly proportional in this case, to force. As one increases, the other increases in the same way. The other thing we saw, though, was how acceleration relates to mass. And we saw the opposite happen, that it wasn't that acceleration increased and that made mass increase. When acceleration increased, the mass had to decrease. And so acceleration is still proportional to something that we can state, but it's inversely proportional to mass. And so we say that it's actually proportional to 1 over, or 1 divided by, mass. Another way to say that is it's proportional to the reciprocal of mass. But all of that is just a fancy way to say they're inversely proportional, which means they do the opposite of one another. As one increases in some way, the other will decrease in a similar mathematical way. When we combine both of these things together, though, it leads to one common proportionality statement, that acceleration is directly proportional to force, but inversely proportional to mass. So in other words, acceleration will increase as force increases, but decrease as the mass increases. So that proportionality relationship gives us almost everything we need to write a final equation. But technically so far, all that is said is that they're proportional. So it means when one increases, the other will increase in the same way. We can't for sure say right now that both quantities are exactly equal. So we're not quite at the stage of developing an equal sign. But if we just take this proportionality statement first, if I take this whole thing here and write it out in a slightly different way, if acceleration is proportional to f over m, that means f on its own is proportional to m times a. It's essentially just taking that proportionality statement and I'm multiplying both sides by m. Just a simple math step. So now we're seeing that F, or force, is directly proportional to the mass of the object and directly proportional to the acceleration of the object. And so it's actually directly proportional to the product of the two multiplied together. Then again, we can't quite say a final equal sign just yet, because when we're just looking at the force on one side and mass and acceleration on the other, we can't say for sure that the units will also work out to produce exactly equal quantities on both sides. But we haven't really talked too much about what a newton really means, but as long as a newton gives us the right unit that exactly equals the units we would be getting on the other side of this proportionality statement, then we can go from proportionality to a final equal sign. So let's think about this. We've got units of kilograms, and mass is in meters per acceleration, is in meters per second squared. Well, we know that force is in newtons, but a newton, we talked about, really is a kilogram times a meter per second squared. So not only are those variables proportional to one another, their units are actually identical as well. And so they end up equaling the same thing on both sides. And so we can actually go from this proportionality statement directly to an equal sign. It's not just that force is proportional to mass times acceleration. We can now say that force is equal to mass times acceleration. Now, if this was a little bit tricky for you to follow and understand, that's okay. You don't need to be able to derive this formula from scratch. All you have to do is be able to understand it and use it in other contexts. In general, though, this is Newton's second law. His law in words says that an object will accelerate proportionally to any external net force. And so that's what we've already seen, that acceleration is directly proportional to force. When one increases, the other does. But it's inversely proportional to mass. So when one increases, the other will decrease in a similar mathematical way. So in the end, though, we arrive at this final overall formula, and F net is, of course, net force, which needs to be in newtons. And remember, newtons needs to require kilograms and meters per second squared. And so that tells us what the units for our mass are and what our acceleration would be as well. And there is a spot just underneath the formula to put in some unit analysis. I already essentially went through what the units are and how they fit together, so I'll let you on your own try and fill in that unit analysis part. But again, it should just be verifying that newtons are what we get for force on one side, and they're truly just giving us kilogram meter per second squares on the other side. Now, if we look at how we use this formula in an example, let's say we know that a 56 Newton net force is being applied to a 26 kilogram box. Well, we know that if a net force is being applied, it must be accelerating, so our follow-up question is just how fast is it accelerating? Well, it's a simple stating givens and required situation, so we can say what we know, F net is 56 newtons. Now, notice I'm not really concerned about the full vector version of the force. I'm just writing down what its magnitude is, because in the end, we're not even really concerned about what direction this acceleration is in. We're just trying to find the rate of acceleration, just a magnitude. But along the way, we're going to use mass as well, 26 kilograms, and we are looking for acceleration. That's our required quantity. We can always start with this formula. And again, technically it is true that the vector versions of these variables are equal to one another, but we're just going to be focusing on the non-vector versions of them as we actually go through this. So more specifically, we could rearrange this formula and say that A is actually equal to F net divided by our mass. So if we take our net force of 56 newtons, we divide by 26 kilograms, and when we do that, we get 2.2 meters per second squared. And again, how was I so sure that it would be meters per second squared? Well, partly because I knew it was an acceleration. But also, and I'll just pull this out as a little aside, we've got newtons on top, so it's like kilogram meter per second squared is our unit on top, and we're dividing by units of kilograms on the bottom. So when we do that, the kilogram units are canceling one another out and leaving us with just a meter per second squared unit. So of course, then we would just write a final therefore statement, which I'll leave for you to write, that therefore our box is accelerating at 2.2 meters per second squared in whatever direction that net force was in. Because we weren't specifically told what direction the net force was in, we can't actually say what direction this acceleration is happening, but we know that they are always in the same direction as one another. Example 2 is one I'm going to leave and go through in class, but I encourage you to try and do it first all together. So even before we get to it, we can talk about the idea behind it. A 2.3 kilogram box slides across the floor and comes to a stop in 3.4 seconds. And we also know how far it slides. So here we're given the box's mass, but we're also given some information that comes from our kinematics unit. We're given some information about how long a motion took. We know how far it went, so we have a displacement. You could also think a little bit about if there's any velocity information that we know. And so for example 2a, again, I'll leave this for you to try first, but we're asked to find the acceleration. So the hint I'll give, and we'll go through this eventually in class, is to use kinematics. Use things that we know from kinematics first to find the acceleration of the box. But then once we can learn acceleration through kinematics, that will help you to answer the force-based question in part B below.